the very first and the most important were the crystalline and amorphous. Which of the two have a sharp melting point? Has a sharp melting point? Which of them is isotropic in nature? Uh, Quartz glass is what type of a solid? Okay. Which is a long range order? Which is anisotropic in nature? Be spontaneous in answering, because you get questions as simple as that. So these should not, in fact, these should help you in getting extra time for the other questions. Then we talked about, based on the molecular forces, there are different types. So I'm not going to discuss them again. Ionic, you have covalent, you have metallic, and you have molecular. And when you talk about the molecular solids, you again have different types that you discuss. You have polar, you have non-polar, and you have hydrogen bonded solids, right? This all we had done last time. Some questions from this. Argon is what type of a solid out of these four? Or let me just, silver is what type of a solid? Silver. Silver is what type of a solid? Simple silver. Metallic. So it will be metallic, alright. If I talk about NaCl, I don't expect a wrong answer in this. Then if I talk about HCl, which HCl, so the preference will be given to, otherwise you can talk about HCl to be an ionic also, you can talk about this. Alright, if I talk about H2, solid, H2, it will be simply non-polar. Wherever you have a network, you generally put it in a covalent solids. Last time I think Divya pointed it out. So what you can have is, you can have covalent network solids when there is a network kind of an arrangement. So that is a good demarcation. Alright, then there is another, then we started discussing the A type of solids. Remember, A type of solids, in which we discussed again 4 types. What were those 4? The ones that we had discussed last time. You had a simple cubic unit cell, SEC, then you had, that's generally termed as P. This is the Hermann-Marguin notation. Please pay attention here. When you talk about simple cubic unit cell, you talk about the Hermann-Marguin notation, which is simply P. P stands for primitive unit cell also. It's a primitive one, and remember that in case of simple cubic unit cell, the number of atoms per unit cell is equal to 1. Okay. Then you have BCC, that is body centered cubic unit cell, and in body centered unit cell, the general notation for this is I. Alright, body centered, and the number of atoms per unit cell for this is equal to 2. Then we discussed face centered cubic unit cell, in which you have atoms at the corners as well as at the center of the faces of the cube or the unit cell that we are talking about, and that has a notation F. Then you also talk about end centered cubic unit cell. End centered is the one in which there are atoms at the center of any 2 opposite faces. Atoms at the center of any of the 2 opposite faces. It can be this and this, it can be top and bottom, it can be front and back. So any 2 opposite faces. Like I had given you an example of an HCP, and I asked you the contribution of the number of atoms per unit cell before I left last time in the last class. So you have, I had drawn this was an HCP, and I told you that in this case you have atoms at the corners. So if each of the corners had one unit cell, each of the corners of the unit cell had 1 atom each. I told you that there are 3 atoms wholly within, and it was an end centered kind of an arrangement because it had an atom at the top and at the bottom. So this is what it was. Okay. So if I tell you that if you have to find out the number of atoms per unit cell, see the ones which are wholly within the particular unit cell have a total contribution. So if 3 atoms within, that means the number of atoms per unit cell from within, or like from within the unit cell are having a total of 3. Then you have one at the top face and one at the bottom face. So that is like half contribution, because it's a sphere. So half of the sphere will be lying within one unit cell and half will be in the other, which is above. So it will be half per face. So how many faces do have it in the center? So you have it on 2 faces. Then the main thing comes when you talk about the corner. And when you talk about the corner, think of the shape that will be repeated again and again. Because it was hexagonal, it will be the hexagonal shape which will be repeated again and again. So in this case, you can just quickly draw. This is what I did quickly last time, so I wanted to revise this. So you have a hexagon here and you have another hexagon here if I am concentrating on this corner. So you have a hexagon here, a hexagon here, and then another hexagon here. So if 3 are sharing this corner, there are 3 above it also. So that means 6 unit cells are sharing one corner. Clear? 6, because 1, 2, 3 that you can see here, 3 are placed exactly above this. So it will be 1, 2, 3 and 4, 5, 6 above. So that means if 6 unit cells are sharing one corner, the contribution of this sphere, कितना sphere एक unit cell के अंदर आएगा, because it's a entire sphere. So it will be 1/6 into the total number of corners, क्योंकि एक corner से 1/6 contribution आ रहा है, and you have a total of 12 corners. So that ways you can have a total of 6. So the answer turns out to be 6 atoms per unit cell. This was one of the problems given. You can be similarly given any other unit cell and you can be asked to find out the number of atoms per unit cell. So there you just have to lay emphasis on faces and corners especially, because whatever is within will be a total of that number only getting added up. Another thing here is, say if I am talking about a face centered unit cell, look up all of you all. I told you a unit cell is a complete representation of one molecule. Say if I am talking about NaCl, one unit cell will be completely representing one NaCl unit. If I talk about CO2, solid CO2, then one unit cell is a complete representation of one CO2 or CO2 unit. Alright, if I talk about a silver atom, then again it is not like if you have 4 atoms per unit cell. So it is not like you have 4 Ags there. One unit cell is a complete representation of one Ag atom. Say if you are talking about the silver solid, you getting the point? So and then there are certain things, you know the definition of unit cell and crystal lattice. Those are the most important ones before even you start talking about solids. You should know what is a unit cell, that is the smallest 3-dimensional unit which when repeats itself in 3 dimensions give you the entire crystal lattice. Okay, so and the other thing is like crystal lattice is an enlarged form of your crystal lattice. It is an enlarged form of your unit cell only. Okay. Another thing that I wanted to tell you here is that if I tell you that I have a solid which has 2 atoms A and B, A is occupying all the corners and B is occupying the face centers, then what will be the formula of the compound? You get questions like this, and it can be various permutations and combinations that you can get. So remember that corners, the contribution that is coming from the corners is, if you talk about naphthalene, it is going to be a non-polar, because naphthalene is the structure. You have naphthalene, so you have naphthalene in this form. Alright. Then here when we talk about this, and naphthalene, if the naphthalene is existent in a complete network kind of a structure, then you can put it in covalent as well. So now that depends on choice as to what kind of an option do you get in the choices. If you have only non-polar, you will be selecting non-polar. If you have non-polar and covalent, then you should go in for covalent as well. because naphthalene was put up as a separate choice. Okay, so now we were talking about, because A is occupying only the corners, so then in that case, you know, the corner contribution was 1/8 into the total number. That is according to your simple primitive arrangement. So that means your A will just be 1, and B is occupying face centers. That means in that particular unit cell, it's half into the total number of faces, that is 6, because faces का contribution कितना आता है? It's a big sphere, आधा sphere एक unit cell में और आधा sphere will be in the other unit cell. So the contribution will be half into 6. So that means the formula of my compound will be AB3. Okay. Then another thing is that I did tell you that we talked about some 4 kind of cubic unit cells, like we did talk about SCC, BCC, FCC, right, and N-centered unit cells also. But how many A-type lattices are there? Because these are your things that are talking about the lattices. How many A-type lattices are there? There are 14 Bravais lattices. And remember that why do we talk out of these 14 in specific only for, why do we talk out of these 14 lattices? We talk only about SCC, FCC, BCC in particular. That is the reason I told you that out of the entire periodic table elements, you have 80% of the elements existing in either of these 3 or 4 forms that you have done. Okay. Then when you talk about the 14 Bravais lattices, remember that each one of them are distributed over 7 crystal systems. There are 7 crystal systems according to the arrangement. See, when you are talking about the unit cell in totality, it is not necessary that all the 3 edges will always be the same. It can be a cuboid as well, depending upon the arrangement. It can be having, so these are known as the edges of the unit cell. Say A along the x direction, B along the y direction, and C along the z direction. And then the angles that they are making with one another are generally termed as alpha, beta, and you have gamma. That is along these angles are known as interfacial angles. Interfacial angles means the angles which are in between 2 faces of a crystal. Okay. In fact, your solid state is nothing but is related to the study of crystallography, because इससे आपको information किस चीज़ की मिलती है? About the kind of structure that a crystal is possessing. So this is a part of crystallography, and there are 2 laws in crystallography. I am talking about the first law first. The first law of crystallography talks about the constancy of interfacial angles. It talks about the constancy of interfacial angles. Which angles am I talking about now? The alpha, beta, and gamma. That means if a unit cell possesses a particular alpha, beta, and gamma, these angles will be repeated throughout your crystal lattice. So that means once a unit cell, it's just an expansion of your unit cell and crystal lattice relationship. The first law of crystallography states that you have the interfacial angles remaining constant throughout. That is why it is also known as the law of constancy of interfacial angles. And you understand now what alpha, beta, and gamma is? Alpha, beta, and gamma are the angles between 2 faces. So this and this face, this and this face in your classroom, and you have what is left? This and this face. So the 3 angles which are possible between the 3 faces, those are basically constant, and that is what is stated throughout the crystal. That is what is stated according to the first law. Now when I am talking about the 14 Bravais lattices, I am just telling you that they are distributed over 7 crystal systems. Now the entire table is important because each of the crystal system has different structural properties. Structural मतलब A B C का जो relationship है, and alpha beta gamma का जो relationship है, that is unique for each of the crystal systems. So I will just quickly talk about those crystal systems and you can memorize it right here right now. What you have is, you can remember C Tom HRT. C Tom HRT. You can remember this. These are the 7 crystal systems. What are those? Cubic, then you have tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral and triclinic. Look up and repeat it. The table is given in the books, no need to copy the table. All of you all have your textbooks, so it is given in all the books generally. So just look up, because it is important to remember. I'll just take 2-3 minutes and you'll memorize it right here. What you have is C Tom HRT, and what you have in this is cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, triclinic. Clear to everyone? Remember that this is the most symmetrical and this is the most non-symmetrical or unsymmetrical, right? This and this have that kind of an extreme. So a little different arrangement that your books, but you can remember C Tom HRT. And do you want me to repeat the names again? No? Sure? This one is for tetragonal, only the T has a disc. This is for triclinic. Another thing, this rhombohedral is also known as trigonal, but it would have made it further complicated with 3 T's. I did not put it. Rhombohedral is also known as trigonal. This is tetragonal and this is your triclinic. Now for the arrangement of the edges, you have A is equal to B is equal to C here. This is the most symmetrical and this is the most non-symmetrical. So this will be A not equal to B not equal to C. Clear? Then here just put A is equal to B but not equal to C. Right? In orthorhombic, generally the ones which are ending in ik have none of the edges the same. So you have A not equal to B not equal to C. And now what you do is just repeat these 3 in this order. First copy this and then this. Do you get it? So this is monoclinic, A not equal to B not equal to C, hexagonal, A equal to B but not equal to C, and rhombohedral has A equal to B equal to C. Because you can get MCQs based on it and the table is not that difficult to learn. Then we come on to the interfacial angle relationship. So here you know alpha will be equal to beta will be equal to gamma, which will be equal to 90 degree. And for triclinic, you know none of the angles will be equal, because I told you this is the most symmetrical, and here you can actually have alpha. In fact, symmetry we should not be talking of here, because alpha is not equal to beta, is not equal to gamma, is not equal to 90 degrees. And then look up, for the first 3 cases the angle relationship is the same. So for cubic, for triclinic and orthorhombic, the angle relationship is the same. So you have alpha equal to beta equal to gamma equal to 90 degree, alpha equal to beta equal to gamma is equal to 90 degrees, and then you have here you have alpha equal to gamma equal to 90 degree, and beta is not equal to 90 degree. And beta is not equal to 90 degree. And for the hexagonal, you have alpha equal to beta is equal to 90 degree, and gamma is equal to 120 degrees, and hexagonal as it is, you can think of the angles there. And then for rhombohedral, you have alpha equal to beta equal to gamma but not equal to 90 degrees. So a little bit here that you will have to think about. Out of these, orthorhombic has P, I, F, C, all types of cubics, all types of cubic unit cells. That means not all type of lattices. P stands for simple cubic lattice. Remember that the arrangement will be according to this for the unit cell, but it will be having atoms only at the corners. I means body centered, that means apart from the atoms being present at the corners, the atoms will also be present at in the body center. Then F is your face centered, C is your end centered. C is your end centered. And similarly for this you have P, I and F, and then for the others also you have other types of units, lattices which are available. When you count all these lattices which are given, all these lattices, like 3 are possessed by cubic, rhombohedral has a simple P, and hexagonal also similarly. Exactly, I'm just forgetting right now, but here you can remember that when you total it up, this is not that important as much as these dimensions are. So the dimensions, the spatial dimensions can be easily remembered. Then when you talk about each of the crystal lattices that are possessed by each of your crystal systems, the total of this is 14. So you basically say that these 14 lattices are distributed over 7 crystal systems. Okay, I repeat, these 14 lattices are distributed over 7 crystal systems. That you can understand, and I just give you exactly 1 minute to learn this table right here, right now. For cubic, the best example can be NaCl, or you can talk about zinc sulfide, zinc blende, copper. Then for tetragonal you have tin and tin oxide as an example. For orthorhombic you can have rhombic sulfur as an example, because sulfur has different forms. It has rhombic sulfur also, and monoclinic sulfur is also there. So for monoclinic, again you remember one example for sure, that is monoclinic sulfur. For hexagonal you can have zinc oxide, cadmium sulfide, or graphite. You know graphite has a hexagonal sheet kind of a structure. So hexagonal has an example of graphite or cadmium sulfide. Then for rhombohedral you can have calcium carbonate or cinnabar, that is your HGS, and for triclinic you can have potassium dichromate as an example. Done with the table? All of you all? What are the 7 crystal systems? C-term, HRT, and then the table can be easily drawn, or you can just remember it. I tell you, if you draw this table at least twice or thrice on your own, you will be able to memorize it forever. Then you will not be able to forget it. And remember, for hexagonal it is alpha is equal to beta is equal to 90 and gamma is equal to 120, and the one before that has alpha gamma equal to 90 and not equal to 90. Yes. For tetragonal, I told you it's like tetragonal is the first one, that's white tin or tin oxide, lest I get confused. Alright, so then you talk about the spacings, okay, in the different arrangements which are possible. Just look up for a minute and I'll just explain this quickly. Look up. See, if I've already told you, if I talk about atoms, the atoms are just closely placed to one another, and remember that if I am talking about simple cubic unit cell, then also the atoms are like touching each other. I last time told you that this is only a point model when you are actually drawing the here, right? This is only a point model. Otherwise, in reality, what is it? It is like this. The atoms are touching each other. So remember that whenever we draw close packed structures, the atoms are always touching each other. Okay, so if I talk about atoms to be placed, there is only one possibility in one dimension, that the atoms will just be going like this totally, right? If I repeat, I am saying that if I am talking about the atoms to be placed in moving in one dimension, the only type which is possible is like an A type of lattice. A, there is no discrepancy. See, we will move on to B, we will move on to B only when there is a change in the arrangement. यहाँ पे तो possibility और कोई है ही नहीं in 1D, so it will be A type lattice for any atom if I am just moving in 1D. The only thing is now when I talk about a two dimensions means अभी मैं इस direction की बात करी थी, अब मुझे I will have to move in the other direction as well, other dimension. So now I will be moving about Y. Understood? A type समझ में आया, 1D में तो और कोई possibility ही नहीं है. The atoms would just be touching each other, atoms, spheres, molecules, ions, radicals, whatever you talk about, they would just be touching each other like this. So you have only one possibility, that is A type of lattices. Now if I talk about the two-dimensional case, here you can place the atoms, there are two possibilities. Either you place the next, because ab ek aur you will have to place another line of atoms above in the y dimension. So aise badhne ke liye I will have to put it here. So now there are two possibilities. One is you put the atoms one on top of the other, and the other is you put them in the depressions. You put them in the depressions. Now here let me just talk about the first case first. That is, I am just putting the atoms one on top of the other. They are not overlapping, they are just touching each other. So look at it like that only. Okay. So now when you join these centers, and the other possibility is, let me just talk about the other possibility also. This is the first possibility, in which your next layer, no need to draw this, it's given very beautifully in the books. You may fumble while drawing and make a mistake, then rub it, draw it, cut it, draw it again. Don't do that. So here you have, okay, this kind of an arrangement which is possible. Then in the next you place it on the depressions. So in the when you place it over the depressions, it will be something like this. Okay. Now you are placing it in the depressions. Seen? Now when you actually do this and join the centers of these atoms, can you see what's getting formed? Square. So this is known as a square close packed structure, and remember we are talking only about the two-dimensional case. It is a square close packed structure. Now when I am talking about this case, and if I join the centers, in this case when I join the center of the nearest neighboring atoms, then I get a hexagon. So this is kind of a hexagonal close packed structure, but this is only in case of 2D. Now when I move in 3D, what is the possibility? Now that means I have moved along this direction, that was 1D. I have now moved along this direction, that is my 2D. Now for 3D I will have to move here above it. So now I am not drawing, I will just place it on top of this. Okay. So now imagine that for this particular type, which is the square close packed 2D structure, iske liye if I place a similar kind of a sheet above, just above it, which is the best possibility found naturally, what you find is that you have A type, A type, A type, A type, A type layer. So it basically forms an A type of a lattice only, forming a perfect kind of a cube when you are joining the centers. Understood? This is a square close packed structure, and I am now placing another sheet on top of it. When I am placing another sheet on top of it, what do I get? It's a perfect one layer, and all the layers are just the same, because 1D mein ho gaya, 2D mein ho gaya, now I am moving towards 3D. So it is like a cube which will be formed, and that would be known as a total of A type of lattices. Now for the next case, for the other case of 2D that I have here, what can I do is, I can actually place atoms on the depressions that I have here, alright. So if I start placing them, see here, then I will have atoms here. My diagram is a little weird, so excuse me for that. So that means you are placing the atoms in such a way that the voids or these spaces in between will be getting covered. You getting the point? So if you check up, there are two types of depressions. I am very sorry for my drawing, but then just look carefully. It will make you understand that purpose will be solved. So you have two types of depressions when I am joining these circles. There is an upper triangle and there is a triangle which is facing towards the down. The apex of the triangle is facing downwards. So when I cover this with a sphere or an atom, then this void, the upper facing, is covered by 1, 2, 3 and 4 triangles. So the void or the space which is left in between 4 atoms, that is known as a tetrahedral void. Okay, and when I keep covering these tetrahedral voids, can you just see, I'll just or am I confusing this? Let me just draw it again quickly. I am just drawing, say this is my A type. Now I am placing the next layer in the depressions. So this is coming like this. This is coming like this. Let me just concentrate now here. You got it? I am drawing the HCP of the 2D. Now I am trying to cover up the tetrahedral voids. I don't even have a different colored pen, otherwise I would have shown. It's coming like this once, and the other one is now covering the other tetrahedral void, and the next one is covering the other tetrahedral void. समझ में आया? So अब इस case में this void which is covered has how many spheres around it? 1, 2, 3 and 4. So the void or the space which is left in between 4 atoms or spheres, that is known as a tetrahedral void. Now what will happen to the next case? While covering the tetrahedral voids, can you look at this circle, dotted one, this dotted one and this dotted one. Alright, and then you have 1, 2, 3 here. So this one, now the one that I am going to darken now, I am just moving this now. Now I am darkening this one. It is surrounded by 1, 2, 3 and the solid ones, the solid spheres that I have drawn, 4, 5 and 6 spheres. So this particular space is now being covered by 6 spheres, and this is known as an octahedral void. So the space which is covered by or occupied or surrounded by 6 atoms, that is known as an octahedral void, and the one which is surrounded by 4 spheres is known as a tetrahedral void. Is this thing clear to everyone? So basically you have different types of voids. You have a tetrahedral void which is surrounded by 4 atoms, octahedral void which is surrounded by 6 atoms, and you have also a simple cubic void which is wholly present within your simple cubic unit cell. You know a simple cubic unit cell is this one. It is a simple cubic unit cell which has atoms at the corners. So even when they are like touching each other totally, so there is some space which is left in between. So the cubic hole is the hole which is within, totally within the simple cubic unit cell. Got it? Now from numericals point of view, there is an important thing that say if your atom or the crystal system comprises of n atoms, there are closed packed structures. You can have a CCP structure or you can have an HCP structure. Okay, when you talk about a CCP or an HCP structure, remember that the total number of octahedral voids, will be equal to the number of atoms which are possessed by the system. Okay, the total number of octahedral voids will be equal to, say, n, if n atoms constitute a particular solid, and the total in a closed packed structure in it, and the number of tetrahedral voids will be equal to twice that number. The number of tetrahedral voids will be equal to twice of that number. Okay, just remember this, and I will give you numericals based on it quickly. I repeat, if n number of atoms are possessed by any system, so then the number of octahedral voids is equal to n, that is equal to the number of atoms only, and the number of tetrahedral voids is equal to 2n. And remember, if I am talking about the lattice positions or the crystal sites या lattice positions की बात हो रही है, तो that is the number of lattice sites will be equal to n only. Why? Because जितने atoms हैं उतनी तो lattice sites थी ही, then only a solid will be formed. So the number of lattice sites, if they are given, those number of lattice sites will be equal to the total number of atoms only. This clarity is there. The number of then the number of octahedral voids will be equal to n only, and the number of tetrahedral voids will be equal to 2n. A simple question before I move on to the other 3D pattern. If I have a solid comprising of n atoms occupying the closed packed lattice positions, where or let me just say, a atom in a compound occupies all the lattice sites, alright, and B occupies all the tetrahedral sites. What is the formula of the compound? AB2. Why? Because A occupies all the lattice positions. So if I am saying it occupies all the lattice positions in your solid, means that it occupies n number of positions. What will B occupy? It will occupy 2n number of positions. Why? Because B occupies all the tetrahedral voids. So the correct formula for the compound will be AB2. Alright. Okay. Now if I have another compound XY, where Y occupies all the octahedral voids and X occupies twice the number, no, alright, Y occupies, I said, octahedral voids, and X occupies 2/3 of the total number of tetrahedral voids. X occupies all the octahedral voids, so, and X occupies twice of 2/3 of the total number of tetrahedral voids. So I know tetrahedral voids are 2n, octahedral voids are n. So this will be x of 4/3 y. So that will be x4 y3. Clear? This way you can actually get the formula of the compound just by knowing the arrangement of the atoms of any particular compound. Okay. Now I talked of, in 3-dimensional case, I talked of one layer of one type, then I talked of, say, another layer on its type. If I place the same layer, if let the first layer be A, then the layer that was placed on the depressions, let that be B, and now there is another layer which can again be placed in such a way that that is similar to A again. So this will be AB kind of an arrangement then. That's too small, so I'll write it in a bigger form. Say if I am placing one layer of an atom, that was one sheet. If I place another sheet on top of it, which say was occupying the voids, okay, just a representation. So this is a different type of a layer, this was a different type of a layer. Understood? वो पीछे वाला जो the board that I rubbed just now had your one layer 2-dimensional HCP was there, and I placed the third dimensional layer on top of the depressions. I started filling up the tetrahedral positions first, and the octahedral void was also generated. Why? Octahedral was in between 6 spheres and tetrahedral was in between 4 spheres, right? So the upper depression and the lower depression. अब वो एक layer थी और ऊपर जो मैंने dotted वाला बनाया था वो दूसरी layer थी. So if this was A type, I am naming the other layer as B type. Now if again I get a similar layer above it which is similar to the first one, then again that will be A. Again depressions में दोबारा से place करेंगे तो I'll get a type which is like B. So this AB kind of an arrangement corresponds to hexagonal arrangement which is known as HCP. Okay. Now there is also a possibility that I could have placed again the third layer. I'll just take up the questions. The third layer on the depressions of the second layer. फिर उस केस में क्या होता, अगर ये A है और मैंने second उसके depressions पे place कर दिया और अब मैं third ऊपर एक और लगा रही हूँ layer that is on depressions of this, so then this would have been B, and third का nature would have been absolutely different than the first, so you call it C, and then this repeats again. Okay, and then you have on depressions. So then this repeats ABC, and this is known as the CCP kind of an arrangement in 3D. So when I talk about the 3-dimensional arrangement, I talk about HCP and I talk about CCP. Remember, HCP has what kind of an arrangement? Layers. अब ये AB क्या है? ये layers हैं. ठीक है? उससे पहले जब हम 2D में बात कर रहे थे तब we were talking about the lines of the atoms. Now we are talking about the sheet, complete sheet. So it is AB type, then it is HCP. If it is ABC type, then it is CCP. Now, ma'am, are the tetrahedral voids located in the corners of the cube or in the edges? See, the tetrahedral voids can be decided by looking at the positioning of the atoms. It is given in NCERT also. When you look, if you talk about the tetrahedral void and if you have a simple cubic unit arrangement, then in that case, you cannot talk of the tetrahedral voids to be just placed at the corners. Alright, there is a possibility at the edges as well as on the faces when you talk about the tetrahedral voids, because the tetrahedral voids are the ones which are surrounded by 4 atoms, and the octahedral are the ones which are surrounded by 6 atoms. So according to the positioning of the unit cell you can actually decide, and the diagrammatic representation of this is beautifully given in your textbooks, the NCERT textbook that you have. Just check it out, it's given in a red box. Okay, fine. Then the next question is, please explain AB2 again. This is one of the easiest questions that you can tackle, so it's good that you are asking again. Remember that I told you for the AB case that A is occupying all the octahedral voids or the lattice positions. एक ही बात है. अगर मैंने बोला A is occupying all the lattice positions, मतलब lattice positions जो है that will be equal to the number of atoms. So that means A, number of A atoms will be n, because the question that I stated was that A occupies all the lattice positions. So A occupying lattice position means number of A atoms are n, क्योंकि lattice positions will always be equal to the total number of atoms. And then I must have stated that B occupies the tetrahedral voids. So tetrahedral voids are always twice the number of atoms. So that is why the number of atoms for B will be 2n. So what will be the formula of the compound? N and N can get cancelled. So what you have is, the formula of the compound is AB2. Okay. In the last question, how did the formula come as x4y3 from x4/3? Alright, the last question that I stated was that consider a compound having x and y atoms where y occupies all the octahedral voids. So that was n, because the total number of octahedral voids is equal to n, and x occupies twice 2/3 of the total number of tetrahedral voids. Now the total number of tetrahedral voids will be equal to 2n. So x will be equal to 2/3 into 2n, that is 4/3n. Of course you cut the n and n, so the formula that you have actually written is 4/3y, that's it. Now in order to get a stoichiometric compound होता है जिसके अंदर number of x atoms is an integral number और y भी एक integer है, the number y का भी जो coefficient है that is an integer. So for that I multiply the entire formula or the subscripts with the denominator, so that is 3. So then when I multiply this by 3 and this 1/3, so what I get is, I get x4y3, and I do this only to get a stoichiometric compound x4y3. I just explain, stoichiometric compounds वो होते हैं जहाँ पे अगर एक एटम मेरा एक इंटीजर फॉर्म में है तो दूसरे एटम्स भी इंटीग्रल फॉर्म में ही है. That means for every 4x I will have 3 y's in my molecule in 1 mole. Yes, CCP is cubic close packed structures and HCP is a hexagonal close packed structure. But remember here one thing, that the number of octahedral voids for both of them will be n, the number of tetrahedral voids for both of them will be equal to 2n. So this formula is like a general one. Another thing that I'd like to point out here is that CCP has an ABC type of an arrangement. ठीक है, एक हमने यूनिट सेल करा था FCC का जो अरेंजमेंट है that is also ABC type. So how do you compare the two? CCP is kind of a crystal lattice, तो हम बोल सकते हैं consider that a CCP has an FCC kind of a unit cell. ठीक है, CCP has an FCC unit cell, ऐसे बोल सकते हैं. तो अभी तक what did we do? We just did the Bravais lattices, 14 Bravais lattices over this 7 which are distributed over the 7 crystal systems, and here we are talking about different types of arrangements which are possible. So in 1D there was only one arrangement that was possible, AAA type. Just for the arrangements, in 1D what was the only type of lattices which were possible? A type. Alright, when we talked about 2D, we had a square close packing. Square close pack कैसे आई थी? A के ऊपर जब A लगाया था as it is in 2D. In 2D, that means I am talking about only 2 dimensions, and when I placed it over the depressions, Then I got a hexagonal close pack structure in 2D. फिर 3D के केस में I picked up the square close pack first, क्योंकि 2D के ऊपर 3D की layers लगेंगी ताकि हमारा वो पूरा 3 dimensional बने. So one sheet over another sheet over another sheet. So this was in 3D you get one from SCP, that was simply जो 2D SCP से आई थी, that was simply A type. A. So that was a cubic closed structure, pack structure, which was just simply A type. And another one that you got from the HCP types were, one was you had AB types, and the other was ABC type. Alright, one was AB type and the other was ABC type. The one which is AB type was your hexagonal close pack structure now, and the layers where you have 3 different types of layers, that is your CCP, which is similar to your FCC also. How can you measure the coordination in FCC? Remember that coordination FCC या किसी भी structure में आप कैसे देखते हो? You actually, what is coordination first of all? Coordination is the number of atoms which are surrounding a particular atom. एक atom के आसपास और surrounding atoms कितने हैं? जैसे for example, if I talk about the very first AA type, इसमें यही था simply 1D का. Remember 1D 2D cases जो होते हैं वो hypothetical होते हैं, तभी कम डिस्कस होते हैं, एंड यू जनरली टॉक अबाउट द 3D केसेस मोर. 1D 2D हाइपोथेटिकल क्यों होते हैं? बिकॉज इन रियलिटी यू हैव नथिंग एग्जिस्टिंग एज इन 1D ओनली, राइट? हियर व्हेन यू आर टॉकिंग अबाउट 1D, द हाइपोथेटिकल केस, व्हाट इज द कोऑर्डिनेशन नंबर ऑफ दिस पर्टिकुलर एटम? 1, so 2. So that ways you decide the coordination. Another thing, if somebody has asked for the FCC kind of an arrangement, an FCC kind of an arrangement will be, you have this, now that's fine. Alright, now if I talk about any particular atom like this, ठीक है, अब इस atom को कितने atom surround कर रहे हैं ये check करना पड़ेगा. Like this is your Na, alright, तो इसके आसपास सारे Cls होंगे. So let's talk about 1, 2, can you see? ये पीछे गया, पीछे वाला कॉर्नर. 2, 3, 4, नीचे भी क्यूब है, और इधर भी क्यूब है. Now look carefully, I am talking about this Na. I have drawn the structures before you, so you know the unit cell. इस Na का coordination number अगर बताना है तो we'll have to look at the number of atoms which can be surrounding it. So if I am just checking it out, for this structure you can check 1, 2, 3, 4, 5, क्योंकि इसको 6 will be here, जो इधर सामने की तरफ, अगर मतलब बोर्ड के बाहर. एक अगर यहाँ पे प्लेस करोगे तो एक you'll have 1, जैसे ये पीछे है ऐसे एक बाहर की तरफ आएगा. Getting the point? If only I were that good, मैं एक पीछे बना के फिर यहाँ से दिखाती. But anyways, do you get it? So you can check the coordination number. So that is why for an NaCl kind of a structure, what you have is 6 Cl minus around each Na plus, and similarly each of the Cl minus is surrounded by 6 Na plus. So that ways you can actually find out the coordination number if you're very sure of the structure. Getting the point? So you just have to just apply a little bit mind, because it's like a cubic close pack structure. So everywhere it will be like that. For like CsCl, cesium chloride, it is 8:8. Each of the Cs plus is surrounded by 8 Cl minus, and each of the Cl minus is surrounded by 8 Cs plus. Similarly for case of zinc sulfide, it is like 4:8. You have 4:8. Each of the Zn2 plus is surrounded by 8 S2 minus, and each of the S2 minus is surrounded. So that is how you actually decide on to the coordination number. That is according to the number of atoms which are surrounding your central atom, or the atom that you are actually considering. Clear? Okay. So The next thing that we can talk about after this is that there is another term which is known as packing efficiency. Packing efficiency is the percentage of the total space which is filled by the atoms in your unit cell. मतलब कितना स्पेस यूटिलाइज हो रहा है यूनिट सेल का. जैसे अगर सिंपल क्यूबिक यूनिट सेल की बात करोगे तो यू नो सिंपल क्यूबिक यूनिट सेल में आठों कॉर्नर्स पे यू हैव योर एटम्स. इन सिंपल क्यूबिक यूनिट सेल you have atoms at all the corners, so उसके बीच में कुछ space होगा which will be left vacant. So in order to calculate, तो जितना space occupied है over the total volume will give you the packing efficiency. So what is your packing efficiency? It is the percentage of total space which is filled. Packing efficiency, the percentage of total space which is filled by the atoms, right? For this we will find out the packing efficiency of 3 generally. HCP और CCP का arrangement is considered to be similar to FCC. तो इस केस में I'll just quickly tell you, if you're we'll calculate the packing efficiency for all of these and simple cubic unit cell, SCC is what you call it. Alright, you will calculate it for the primitive centered cubic unit cell, then body centered cubic unit cell, and then face centered cubic unit cell. If I talk about the simple cubic unit cell, the packing efficiency will be the volume occupied by the number of atoms per unit cell. ये general formula है packing efficiency का. It is the volume occupied by the total number of atoms per unit cell upon the volume of the unit cell. Clear? I repeat it again. It is the volume occupied by the total number of atoms per unit cell. What is the total number of atoms per unit cell for SCC? It is a volume occupied by say how many atoms per unit cell? 1 atom, or 1 atom means atoms are spherical in nature, so volume occupied by 1 sphere upon the volume of the unit cell. Unit cell का volume क्या होगा? If you are talking about a cube, you know what is the volume of a cube? A cube. So that will be like generally A cube. Volume of one sphere would be, what is the volume of 4 by 3 pi r cube? So that is 4 by 3 pi r cube. Alright. Now I will have to, this r refers to the radius of the atom. This r refers to the radius of the atom. So this A can be related to r. And how can it be related to r? Say if you are talking about a cubic unit cell. In a simple cubic unit cell you have atom at one corner and you have atom at the other corner, right? So this is the center of one sphere, this is the center of the other sphere. So this is r and r. So in this case 2r is equal to A. ठीक है, तो जब मैं सिंपल क्यूबिक यूनिट सेल का पैकिंग एफिशिएंसी निकालूंगी, सो दैट विल बी वॉल्यूम ऑक्यूपाइड बाय one sphere. Why one sphere? Because the total number of atoms per unit cell is 1. So that will be 4 by 3 pi r cube upon A cube is 2r ka whole cube, that means 8r cube into 100. This is your packing efficiency for a simple cubic unit cell, and you will find out that this turns out to be equal to 52.4%. Now if you are talking about this, now I talk about the face centered cubic unit cell. Face centered means now I will have an atom in the face also. Alright, ये सामने वाले face पे ही देख लेते हैं. We'll have a full atom in the sphere, atom in the spherical form at the center of the face. So here that means I will be talking about my face diagonal. सिर्फ इसी face पे concentrate करो. So that means what is more important for me is now the face diagonal. What is the total r here? It is r. ये तो पूरा diameter है, so this will be 2r and this again will be r. Now let me just remove the previous one. Now here I have atoms at the corners as well as at the face center. So this one touches the face. So I am concentrating on my face diagonal now. Is that clear? Now the arrangement, now it will be like this. where you have a phase diagonal in between. ये वाला total is A, this again is A, but this is your phase diagonal. So according to the Pythagoras theorem, you know that A square plus A square will be equal to your hypotenuse square. So your hypotenuse, which is R plus 2R plus R, 4R, this is 4R, this will be equal to under root of A square plus A square. So that means root 2 A. And then I need to substitute here in the formula of packing efficiency for the face centered cubic unit cell. I will be considering the face diagonal, right? अगर मैं face diagonal consider कर रही हूँ, so I have just got to know, first of all, what will be the numerator? Now it will be the volume occupied by 4 spheres. Why 4 sphere? Because the total number of atoms per unit cell for face centered cubic unit cell is 4. समझ में आया? The total number of atoms per unit cell, the total number of atoms per unit cell is 4 in case of face centered cubic unit cell. So the packing efficiency will be volume occupied by 4 spheres. So that means 4 into the volume of one sphere, that is 4 by 3 pi r cube upon A cube. Now what is your A? That is equal to 2 root 2 r is equal to A. And how do you get 2 root 2 r? Because you take root 2 on the other side and then multiply numerator and denominator with 2, 2 gets cancelled and you have root 2 in the numerator. So you have 2 root 2 r. So the denominator will be 2 root 2 r whole cube into 100, and this will be around 78%, 74%. Okay, so remember that it is just a measurement that you have to do and you can remember the packing efficiency. It is only that for your subjective paper you may have to know as to how to arrive at this particular expression. Otherwise for the MCQs, remember that you will just be asked the packing efficiency, the ratio of the 3 or whichever has the highest and which has the lowest. The lowest is possessed by SCC and the highest packing efficiency is possessed by FCC, which is 74%. For the BCC now, for the body centered, I will have to now look at the body diagonal. So if I look at the body diagonal, see the body diagonal will be from here to here. Why body diagonal? Because there is an atom right in the center and they are touching each other. So that means I need to concentrate on this body diagonal now. I am just darkening it, and I know that what kind of a right angle triangle can I form. Look at this edge AB and C. So this is my face diagonal BC. BC is a face diagonal. This is my edge of the unit cell. So this will be my A. This will be my root 2A, and this again is like, this is 90 degrees. So this is again a right angle triangle. So using the Pythagoras theorem, I can easily find out AC, which is the body diagonal. What will it be? That will be AC will be equal to, you can find out easily, this will be A square plus 2A square. So that will be equal to under root of 3A square. So that will be equal to root 3A. And again I will have one atom here, another atom in the body center which is wholly within, and another atom at the corner. So R of this, 2R of the body centered atom and R of the other corner one. So the body diagonal is again equal to 4R. So this time my A is equal to 4 upon root 3 R. Okay, so when I move on to the BCC, the packing efficiency will now be, what will be the numerator? The volume occupied by 2 spheres, because the number of atoms per unit cell for body centered cubic unit cell is 2. So that means 2 into 4 by 3 pi r cube upon A cube, और A क्या है मेरा? 4 by root 3 r. A is r 4 by root 3 r. So that becomes equal to 4 by root 3 whole cube into r cube. So then r cube gets cancelled and you can easily calculate it to be 68%. Okay. So please remember this expression, and arriving at it was not that difficult because you understand mathematics really very well. So now there is a question that can we have ABCD type of a solid. See, naturally whatever we found till now was like generally AB and ABC only. But when newer and newer solids keep developing, there is newer and newer kind of modifications also which is made to the classification. So I never say no to anything. So there is a possibility, but by and large generally naturally occurring solids are found to be only in two types of an arrangement. One is the CCP which you've done, that is ABC type, and the other is the CCP which is the ABC type, and the HCP which is AB types. Okay. Now after the packing efficiency, please remember now from the numericals point of view, remember that we have now done the relationship between the edge length and r. R is the radius of the atom and A is the edge length of the unit cell. So please remember this relationship also for FCC, BCC and SCC. SCC is simple, A is equal to 2r, right. For BCC, A is equal to 4 by root 3r, or r is equal to root 3 by 4a, the way you feel comfortable. And then for FCC, A is equal to 2 root 2r, right. So this expression also needs to be remembered for the numericals. You will have very simple numerical from solid state. All you have to do is just apply a little bit of the mind, that's all. So you should make that available. What you have is FCC is A is equal to 2 root 2r, BCC A is equal to 4 by root 3r, and SCC is equal to A is equal to 2r. Giving you half a minute, memorize it right here. Packing efficiency to yaad hoegi, FCC is 74%, BCC is 68%, SCC is 52.4%. Formula yaad ho gaya. It is packing efficiency is volume occupied by the total number of atoms per unit cell. ऐसे देख लो. और atoms क्या है, sphere है, upon the volume occupied by one unit cell. And then this relationship also is very important, that for FCC A is equal to 2 root 2r, for BCC A is equal to 4 by root 3r, and for SCC it's the simplest. Another very important thing that you should be remembering is that you should be able to find out the density of any crystal. The formula for the density is simple, so you can just remember that density is equal to Zm upon n naught a cube, where Z is the number of atoms per unit cell. So Z will be 1 for a simple cubic unit cell, Z will be 2 for body centered cubic unit cell, it will be 4 for FCC, it will be 6 for HCP, no, 6 for the hexagonal close packed unit cell that I had shown the other day. 6 was just an example that I gave. So you lay emphasis on simple cubic unit cell, it will be 1, body centered it will be 2, and for face centered it will be 4. So density is equal to that number of atoms per unit cell into the molar mass. Molar mass means mass of 1 mole of a substance upon the Avogadro's number Na or N0, whatever you feel comfortable with. The Avogadro's number is 6.022 into 10 to the power 23 atoms per mole. So the Avogadro's number is there, and A is now the edge length here. A is the edge length. So the relationship may have to be found if your R is given. Okay, because if your R value is given, your A will be equal to 2 root 2R, or it may be equal to 4 by root 3R, or it may be equal to 2R, depending upon what your system is, and then you can easily find out the density. Another formula for density that you should be able to remember is the basic one, that density is equal to mass upon volume, because sometimes you are given mass and volume, find out the density, and then you are asked to find out the number of atoms per unit cell. for any of the questions. So you can get such kind of numericals in your entrance test. So remember that you should be able to find out Z if the rest of the parameters are known. So there are different formulae for density as well. After density we can just talk about say there is something in solid state. It's like you know that there is an arrangement of atoms. Okay, one thing is there is something you must have all done a table for the radius ratios. So I'll tell you what is a radius ratio. Radius ratio is nothing but it is the ratio of the cation to the ratio of the anion. Each of your solid state structures possesses a cation or an anion if you're talking about an ionic crystal lattice. Alright, so there the ratio of the cation to the ratio of anion will be called the radius ratio. Depending upon your radius ratio, you can actually predict the type of the void which is possessed. Like it has 0.0 to 0.225, then you have 0.225. These are the values of the radius ratios, 0.225 to 0.414, then you have 0.414 to 0.732. ये demarcations हैं, so you can remember, and 0.732 to 1 or higher values. Now I mean 1 is generally the limit when your R plus and R minus are just the same. Nowadays it has also been researched upon and you can have higher values of the radius ratio as well. So here this corresponds to a structure which is similar to a trigonal. Here you have tetrahedral. This will be for the octahedral, and the last one for cubic. So this is something that you've done. So you get a numerical based on it also. Generally the tendency for the radius ratios to be put is like you generally get the value, or the value can be easily calculated. It's like a very quick numerical. R plus is to R minus can be calculated. In whichever category it falls, you can predict the type of or the shape. Alright, tetrahedral void is the one you know. What is an octahedral you know. What is a cubic now you know. And trigonal is the one which is surrounded by generally 3. Okay, and the trigonal arrangement you know is like a trigonal planar. Fine? Can I rub it off? After radius ratio, you've memorized the radius ratio. What are the demarcations? 0 to 0.225, 225 to 0.414, 0.414 to 0.732, 732 to 1. Trigonal, tetrahedral, octahedral, cubic. Learned? Done? Okay, then the next thing is, now look at pay attention on the board, because this is something that you have not done otherwise but generally asked. There are something which are known as देखो अब हमारा सॉलिड स्ट्रक्चर है तो हर एक यूनिट सेल के पास एक एक प्लेन है, ठीक है. अब नेचुरली 3 डायमेंशंस हैं हमारे पास स्पेस में, है ना. एक ये है, एक ये है, या बोर्ड से बात करते हैं. एक बोर्ड पे ये x है, ये y है और ये z है. अब जैसे प्लेन ऑफ द बोर्ड इज कटिंग योर 3 एक्सिस एट सम पोजीशन, अभी z को मैं मान लेती हूँ वो 0 पे काट रहा है, x and y is also getting cut because according to this, right? So each of the planes is going to cut your 3 axes at some or the other place. Like for example, I'll just draw it and show it to you. If this is your x, y and this is your z, now coming out of the plane of the board, they are mutually perpendicular to each other, and I draw a plane like this. ठीक है, समझ में आया? तो अगर मान लो ये मेरा एक यूनिट है, आई कॉल 1 यूनिट. 1 यूनिट का मतलब होता है 1 एज लेंथ. ठीक है, समझ में आया? इट इज 1 एज लेंथ. तो ये मान लो इफ इट इज कटिंग दिस एट 2a, ठीक है, दिस इज बीइंग कट ऑलराइट एट 2b, दिस इज b and then 2b, and say let this is being cut at c. मतलब जो भी मेरा प्लेन है, whether that is whatever shape of the plane is, crystal lattice सबसे पहले क्या होता है? It's a symmetrical arrangement of your unit cells. which is like when you repeat the unit cell again and again, उसका हर एक plane 3 dimensional axis को कहीं ना कहीं कट करता है, ठीक है. तो these are known as the coordinates, जहाँ पे wherever it is cutting. When I take down the coordinates, how will I write it? I will write it down as 2a, comma 2b. So it cuts it at C. So what you have is, it is cutting it at 2a, followed by 2b and at C. Now the ratio of these coordinates, look up, understanding is more important. The ratio of these coordinates with their basic unit vectors is known as your various indices. What are these known as? various indices. समझ में आया? मतलब in short, ये कहाँ काट रहा है? 2 पे, ये कहाँ काट रहा है? 2 पे, and this is being cut at 1. So the V's indices are 2, 2, 1. This is your second law of crystallography. Second law of crystallography states that the coordinates which are being cut on the 3 axes are known as the V's indices. The ratio, no, basically look up, सिर्फ समझ लो. वैसे भी अगर इसको याद रखोगे, नाम लिख लोगे तो याद रहेगा. Second law of crystallography is nothing but it states that when your plane is cutting the 3 coordinate axes in different positions, the ratio of those coordinates with the unit vector, ratio है ना ये, the ratio of those coordinate with the unit vector is an integer. It's an integer, and those integers are known as V's indices. This is the second law of crystallography, or also known as the law of rational indices. Some people call it indices, indices, whatever you call it. Okay, this is the law of rational indices which talks about the V's indices. Clear? ऊपर देखो आप, या चाहिए टाइम? 5 seconds. जनरली जैसे अभी ABC की बात कर रहे थे, डायमेंशंस लिखी थी वो 7 क्रिस्टल सिस्टम्स वाले टेबल में. तो जैसे जब हम ABC की बात करते हैं, A is generally along X, B is generally along Y and C is generally along Z. And the way I have cut it here, is just a general example. ठीक है, अब पूछो, हो गया? अभी नहीं, मतलब अब मेरी एक बात सुनो. In a crystal lattice, you have so many planes, and each of the planes will be cutting at different coordinate axes. मान लो अगर एक प्लेन A पे काट रहा है तो दूसरा प्लेन 2A पे काट रहा होगा, तीसरा प्लेन 3A पे काट रहा होगा, क्योंकि सिमेट्री तो मेंटेन्ड है हमारे क्रिस्टल्स में. सो एक A पे, दूसरा 2A पे, 3A पे, 4A पे एंड सो ऑन. तो हर एक प्लेन के डिफरेंट V's indices होंगे, ठीक है. पर देयर इज अनदर फॉर्म ऑफ नेमिंग देम which is known as Miller indices. ठीक है, अब ध्यान से सुनो. मिलर इंडिसेस पता है क्या होते हैं? इट डिफाइंस, अब मान लो अगर मैं एक तरफ इस रूम में, अगर कंसिडर दिस रूम एज टू बी अ क्यूबिक बॉक्स, इट इज नॉट एट ऑल अ क्यूब, कंसिडर दिस टू बी अ क्यूबिक बॉक्स. तो एक वॉल को अगर देखोगे तो थिंक दैट वॉल इज कटिंग इट एट A, थिंक दैट द सेकेंड वॉल इज कटिंग इट एट 2A. लेकिन जो भी प्रॉपर्टी इस वॉल की है वही प्रॉपर्टी विल बी पोजेस्ड बाय द अदर फेस ऑल्सो. एक डायरेक्शन में तो प्रॉपर्टीज, हाँ, तो वैसे अगर, और द नंबर ऑफ एटम्स और द अरेंजमेंट will be the same for each of the faces. So it is better to define Miller indices, which defines a set of parallel planes. Miller indices defines a set of parallel planes, one of which definitely passes through the origin. I repeat, Miller indices defines a set of parallel planes, one of which passes through the origin. अब इससे पहले कि I move on to Miller indices, let me clear V's indices once again. We have different planes in our crystals. Those planes cut the coordinate axis at some position or the other. Okay, So this plane will be cutting my 3 coordinate axes. 3 कौन सी? X, Y and Z. जहाँ जहाँ पे it cuts and forms the coordinates, that will be my V's index. Right? If I take another example, now you tell me the V's indices for a particular plane. It's very easy to tell. Alright. This is X, this is Y and this is my Z. It's a straight line. Okay. Now tell me what will be the V's indices for this? 2, 3, 4. Second law, somebody wants me to repeat this second law of crystallography again. Second law simply states कि हमारा जो plane, we have a plane of a unit cell or a crystal lattice, wherever it cuts my coordinate axis, the ratio of the coordinates with the unit vectors is an integer. That means if I consider one unit along x to be A, one unit along y to be B and one unit along z to be C, then the coordinates for x will be now 2a by A, for y will be 1, 2, 3, 3b by B, for this what will it be? 1, 2, 3, 4, 4c by C. So this ratio is an integer. There is no need to memorize this law at all. Just understand that the second law of crystallography talks about the V's indices, which are the coordinates which the plane is making with the 3 axis. सिर्फ इतना समझ लो, लॉ कहीं कोई नहीं पूछेगा, लॉ का कोई मतलब नहीं है. Sometimes you get the conversion of V's indices into Miller indices. Okay, that is why I am taking it up. Don't want to devote a lot of time. Which one cut the axis? The plane is cutting the axis. AX, ES, plural. ठीक है? The plane is cutting the 3 axes. X भी कट रहा है, Y is also getting cut and Z is also being cut. समझ में आया? All of you all here with me? So here we have A, then 2A. So basically your V's indices are what? 2, 3 and 4. ये समझ में आया? पर V's indices का एक limitation ये है that for each of the plane, because each plane of your crystal lattice will be cutting each of the axes at different coordinates. तो हर एक V's plane का जो numbering होगा that will be different. Say if this is cutting it at A, the other wall is cutting it at 2A. तो इसका अलग नाम है. The third wall is 3A, the fourth wall is 4A. So each one of them have a different name, but the arrangement is the same for all the walls. So in that case, we define Miller indices, which defines a set of planes, one of which definitely passes through the origin. Okay. Now how do you get that? देखो, मैं V's indices बता रही हूँ. I am telling you the V's indices. Like for example, 2, 3, 2. These are my V's indices. मतलब x का coordinate, y का coordinate and z coordinate. These are my V's indices. How do I convert them to Miller indices? Simply, first step, take the reciprocal. Take the reciprocal. What will that be? 1 by 2, 1 by 3, 1 by 2. Okay. Next step में multiply it with the LCM. The second step is multiplied with the LCM. What is the LCM of 2 and 3? 6. So it will be 3. मतलब now you multiply it with 6. So what do you get? 3, 2, 3. So 3, 2, 3 is the Miller index. I will explain कि ये कैसे set of parallel planes होते हैं, but ये conversion समझ लो, it's very easy. Which of the two is better? Miller indices. Because Miller indices define a set of parallel planes, one of which is passing through the origin. ठीक है? अब दोबारा से अगर मैंने कोई V's index दिया जैसे 1, 2, 3. 1 is the coordinate about x, 2 is the coordinate about y and 3 is the coordinate along z axis. दीज आर माई वीज इंडिसेस। इनको कन्वर्ट करना है मिलर में, कैसे करेंगे? फर्स्ट स्टेप, टेक द रेसिप्रोकल 1 by 1, 1 by 2, 1 by 3. Second step is to multiply it with the LCM. So this will be into 6 into 6 into 6 multiplied with the LCM. So what is the answer? 6, 3, 2. So your Miller indices are 6, 3, 2. समझ आया? ठीक है। अब कैसे ये सेट ऑफ पैरेलल प्लेन्स दे रहे हैं, वो भी एक नंबर है, ये भी एक नंबर है। नाउ लुक अप, समझ आ गया? कन्वर्जन समझ आ गया? पेपर में अगर आया तो वही आएगा और कुछ नहीं आएगा, पर अब सिर्फ समझाने के लिए, फॉर योर सेक। क्विकली लुक एट इट। इफ आई हैव अ प्लेन कटिंग एट a इंफिनिटी इंफिनिटी, ठीक है, इसी का जो पैरेलल प्लेन होगा, वही जो मैं अभी बोल के समझा रही थी। इफ इंफिनिटी का मतलब क्या है कि इट इज पैरेलल अबाउट द y एक्सिस एंड z एक्सिस ऑल्सो। ये 2 डायमेंशंस है, इसमें मुझे पॉइंट मार्क करना है, x इज इक्वल टू 1 यूनिट, मैंने मार्क कर दिया। y इज इंफिनिटी, मेरा पॉइंट है 1 कॉमा इंफिनिटी, तो y इंफिनिटी कैसे मार्क करूंगी? y के पैरेलल होगी ये लाइन, क्योंकि y को मीट ही नहीं करेगी। सो इट विल बी दिस, अंडरस्टूड द कर्व। और ऐसी अगर इंफिनिटी इंफिनिटी है तो दैट मीन्स इट विल बी पैरेलल टू z ऑल्सो, करेक्ट? सो देन इट विल बी काइंड ऑफ अ प्लेन, बट एनीवेज समझ आया तो ठीक, नहीं आया तो भी ठीक। इधर a इंफिनिटी इंफिनिटी एक प्लेन है, तो दूसरा प्लेन क्या होगा? 2a इंफिनिटी इंफिनिटी। मान लो अगर मैंने यूनिट डिस्टेंस से पार्ट रखे हैं सारे प्लेन्स। तीसरा प्लेन क्या होगा? 3a इंफिनिटी इंफिनिटी, ठीक है। अब इसका अगर मेरे को मिलर इंडिसेस निकालना है, तो फर्स्ट प्लेन का और सेकंड प्लेन का और थर्ड प्लेन का, ये वीज इंडिसेस तो सबके डिफरेंट है, क्योंकि कोऑर्डिनेट एक्सिस पे तो डिफरेंट डिफरेंट जगह काट रहे हैं। बट व्हाट अबाउट द मिलर इंडिसेस? दैट मीन्स इसका वीज इंडेक्स क्या है? 1 इंफिनिटी इंफिनिटी, ये वीज इंडेक्स है, ठीक है। और मिलर इंडेक्स क्या होगा? सबसे पहले क्या करते हैं? रेसिप्रोकल लेते हैं। सो 1 by 1, 1 by infinity, 1 by infinity. Then you multiply it with the LCM. In this case, the LCM will just not be there. You have 1 by 1 into 1. 1 by infinity is 0. 1 by infinity is 0 and this is 1. So what is the Miller index for this case? It is 1, 0, 0. Got it? अब second case में मैं second plane की बात कर रही हूँ. So the V's indices are 2a infinity infinity. तो इसका मतलब now it should be 2 infinity infinity are the V's indices. Alright, so now इसका reciprocal लेंगे तो it will be 1 by 2, 1 by infinity, 1 by infinity. अब इसको इसके LCM से मल्टीप्लाई करना है, that will be 2 to make it integer. ठीक है, तो जब इसको 2 से मल्टीप्लाई करेंगे तो 0 into 2 भी हो जाएगा, 0 into 2 भी हो जाएगा. So this will be again 0 0 and this will be 1. ठीक है, समझ आया? अब अगर मैं तीसरे प्लेन की बात कर रही हूँ जो उसको पैरेलल ही था, तो 3a that will be 3 infinity infinity. अब इसका रेसिप्रोकल लेंगे, that will be 1 by 3, 1 by infinity, 1 by infinity. LCM 3 है, उससे मल्टीप्लाई करेंगे, so again it will be 1 0 0. So can you see this 1 0 0 is a representation of a set of parallel planes, one of which we are considering to be passing through the origin. समझ में आया? अगर सेम एक एग्जाम्पल देके बताऊं तो यू टेल मी द मिलर इंडिसेस फॉर दैट. यू हैव ए बी सी. ए बी सी के पैरेलल में दूसरा प्लेन क्या होगा? 2a 2b 2c. तीसरा प्लेन पैरेलल क्या होगा? 3a 3b 3c. नाउ कैन यू अप्रिशिएट वीज इंडिसेस क्या होते हैं? हर प्लेन का डिफरेंट. ये एक प्लेन है, ये उसके पैरेलल दूसरा प्लेन है, ये उसका पैरेलल तीसरा प्लेन है. और मिलर इंडिसेस देखना इन सबके सेम आएंगे. Or in all the three cases you will get what will be the V's indices according to the law. The second law is law of rational indices. According to that law, जो भी मेरा coordinate है that divided by the unit vector will give me the V's indices. V's indices will be in this case 1 1 1 or Miller indices will be again 1 by 1 1 by 1 1 by 1 into 1. So either Miller indices will also be 1 1 1. सेकेंड केस में माई वीज इंडिसेस आर 2 2 2 क्योंकि 2a by a 2b by b 2c by c. और इसके मिलर इंडिसेस क्या होंगे? 1 by 2 1 by 2 1 by 2. LCM is 2. So into 2 करेंगे जब, तो you will get 1 by 1, 1 1 1 only. So you will get 1 1 1. So 1 1 1 is representing all the 3. So Miller indices are always better. Okay, next, done with this? Shall I give you a question? What is the difference between the above indices? These indices वो वाली जगह है जहाँ पे आपका plane coordinate axis को काट रहा है. So each of the plane will have a different set of values because all of the planes are not going to cut at the same point. So each plane will have a different values, but Miller indices are defining a set of parallel planes, and that is what I just explained. Now another important law that you should be remembering before I move on to the law. Please look up. Distance. अच्छा, these indices को हम ABC के terms में लिख देते हैं. Miller indices को हम H, K, L के terms में लिखते हैं. Your Miller indices जैसे 1 1 1 थे, so H, K and L. H is for the X dimension, K is for the Y and L is for the Z. So the distance, because you are doing cubic unit cells, distance between any two Miller planes is equal to A upon under root of H square plus K square plus L square, where H, K and L are your Miller indices. A is your edge length of the unit cell. A here is the edge length of the unit cell. 1 unit, मतलब unit vector जिसको हम अभी तक बोल रहे हैं, and H, K and L are your Miller indices. जैसे अभी 1 1 1 1 0 0 या जो भी निकाल रहे हो वो वैल्यूज. तो दिस D इज द डिस्टेंस बिटवीन टू सेट ऑफ पैरेलल प्लेन्स. जैसे अगर ये रूम का एक वॉल इज वन प्लेन एंड द रूम का सामने वाला वॉल इज अनदर प्लेन, तो उन दोनों का डिस्टेंस कितना है, दैट कैन बी फाउंड यूजिंग दिस फॉर्मूला. दैट इज द distance, perpendicular distance between the two Miller planes is equal to A upon under root of H square plus K square plus L square. Alright, another formula is related to the Bragg's law. Have you done Bragg's law in physics? No. Remember, Bragg's law is equal to n lambda is equal to 2d sin theta. Directly formula कर लो. n lambda is equal to 2d sin theta, where d is the distance between two planes, lambda is the wavelength of the incident radiation on your solid. ठीक है? Theta is the angle at which you are getting a reflection. So n is the order of reflection. N is the order of reflection. Basically Bragg's law is to define, जैसे ये हमारे यूनिट सेल सॉलिड स्टेट और क्रिस्टल लैटिस की लेयर्स हैं, तो ये एटम्स है ना, देखो इधर जल्दी, हियर ये एटम्स हैं. तो अगर मेरी इंसिडेंट रेडिएशन ऐसे आ रही है, ठीक है, इफ माई इंसिडेंट रेडिएशन is coming like this, then theta is the angle that your incident radiation is making with the plane of the solid. ठीक है? And then the next will get reflected when it collides with the atom. Radiation reflect कब होगी? जब वो atom के साथ collide करेगी. So this is your D. D is the distance between two planes. ठीक है? Theta is the angle at which your incident this thing. And then ये जो n lambda है ना, this n lambda is the extra distance covered by your radiation. This is called the path difference. Path difference मतलब वो पहले वाली रे से दूसरी वाली रे ने कितना extra difference cover करा. So that is the path difference. Basically this is equal to the path difference. If you can remember this. Explain Miller indices again. Okay, I'll just explain. These indices हमारे वो वाले indices होते हैं wherever your plane is cutting the three coordinate axes. So say the intercept along x is 2, the intercept along y is 3 and the intercept along z is say 4. Then in that case ये मेरे क्या हुए? These indices, because these are the places where my plane is cutting the 3 coordinate axis. Now in order to arrive at the Miller indices, what will I do? I will take the reciprocal of these 3 numbers and multiply it with their LCM to get an integer. What is the LCM of 2, 3 and 4? 12. So this into 12, this into 12 and this into 12. So that will be 6, 3 4s are 12 and you have. So the Miller indices for these V's indices are 6, 4, 3. But Miller indices की advantage is that it defines a set of planes and V's indices defines each plane separately. कैसे? जैसे अगर मेरा V's indices किसी एक प्लेन का है 1 इंफिनिटी इंफिनिटी, तो दूसरे प्लेन का वो होगा 2 इंफिनिटी इंफिनिटी, तीसरे प्लेन का होगा 3 इंफिनिटी इंफिनिटी. So what do I do to convert them to Miller indices? I take the reciprocal and multiply to make it an integer. So this will be 1 0 0 1 1 by infinity 1 by infinity. Then this will be 1 by 2 1 by 2 1 by infinity 1 by infinity. So that will be again multiplied with 2. So that also becomes 1 0 0 and this will be 1 by 3 1 by infinity 1 by infinity and that will be again multiplied with 3. So you get 1 by 3 into 3, that is 1. 1 by infinity was 0 into 3 is 0 and again 0 into 3, so that is 0. So what I wanted to tell you is that Miller indices have a common notation for parallel planes, whereas V's indices have different notations. Generally you define these planes for the crystal lattices and the crystals. So it is for them only. Otherwise you can actually define V's indices for any damn plane because it will be cutting at some place or the other. Okay, now the Bragg's law, just the formula that I am giving you straight away because of paucity of time. Lambda is the wavelength of the incident radiation, n is the order of reflection. Qualify the equation, otherwise formula याद करने का कोई फायदा नहीं है. N is the order of reflection, lambda is the wavelength of the incident radiation, d is the distance between two Miller planes, theta is the angle at which with the plane. So it is the incident angle only. So no, the incident angle as you do in physics is the angle that it is making with the normal. Here this theta refers to the theta, the angle which it makes with the plane. Okay, so this was your Bragg's law. And then after the Bragg's law, let's move on to some kind of defects. देखो normally जब हमारे पास what do you say solid state structures होते हैं, so they are as it is, some of them possess very low conductivities. Okay, there are different types of in fact conductors and semiconductors and insulators. You have 3 types of substances according to the conductivities. One, you have insulators. In सब में एक, you must have done it in physics, you have a lower level which is known as the valence band and the upper level which is known as the conduction band. If the conduction band is overlapping with the valence band, then you generally call them conductors. If there is little gap such that you provide a little energy and the electrons in the valence band jump to the conduction band, then you call it semiconductors. And if this gap is very very large, so then they are called insulators and they have their conductivities ranging from 10 to the power minus 20 to, no, for all 3 of them, to 10 to the power say 40 or something. The conductivities can go as high as that, ohm inverse, meter inverse. So you can talk about the conductivities like that. But here in chemistry, when you talk about the valence band, remember this is not related to this but a general thing. Valence band is the highest occupied molecular orbitals. आपने configurations करी हैं, तो जितने भी filled levels होते हैं they form the valence band और जितने भी empty होते हैं उसके ऊपर they form the conduction band. Can you understand this? This is just a general thing that you should remember for future science. The filled energy levels in your molecules are your valence band and the filled or the highest occupied molecular levels, highest occupied molecular orbitals बोलते हैं. And then you have here you have the lowest unoccupied molecular orbital, because highest occupied से lowest unoccupied में सबसे पहले जाएगा electron. So the filled levels form your valence band and the empty levels form your conduction band. Okay, next thing is it is very important that if your particular sometimes we cause defects, we produce defects in our crystal, because defects enhances properties like conductivities and other electronic properties. ये समझ में आया defects क्यों करते हैं? ठीक है, अब defects दो type के होते हैं. One is a, now we are talking quickly about the defects and you remember them as another just 15 minutes are left. Please memorize them with me quickly. Defects are of two types. You have point defects and you have line defects. Let me put line above because we are going to discuss point defects. Okay, now line defects are along the entire layer or the lattice. It's a group of lattice points if they are getting distorted or replaced or changed or something is happening to them. Point defects are if any of your atom or ion is being changed or replaced or removed, then you call it a point defect. If there is any deviation from ideality in an atom ion, then you call it a point defect. If there is any deviation in the arrangement of the points, then you call it the line defect. Okay, then you call it the line defect. Clear? Now in point defects you have again two types of point defects. What are those? Stoichiometric point defects and you have non-stoichiometric point defects. Alright. Now there is another type which is also known as impurity defects, in which we put impurities into our solid state structures. Now here for stoichiometric what you have is you have four types. You have vacancy defect. Vacancy में क्या होता है? सुनो, vacancy में we just heat the crystal and atoms leave from its surface. Vacancy में कैसे vacancy create होगी कि lattice position पे सारे atoms हैं. You have n atoms and n lattice sites. So all those are occupying. When you heat the crystal a little bit, what will happen? Some atoms will leave. Vacancy create हो गई. Vacancy defect. Density क्या होगी? Mass by volume होता है. Atoms छोड़ेंगे तो mass कम हो जाएगा. If mass reduces, density reduces. So in vacancy defects, the density decreases. Okay. Then you have interstitial defects. Interstitial defects में क्या होता है कि you have already an atom crystal lattice available with you. There are some interstitial spaces available. Interstitial spaces होते हैं जो atoms के बीच में spaces बच जाते हैं. ठीक है. So the voidal spaces or the interstitial spaces, तो कोई एक constituent atom लाके you put it in the interstitial site. Interstitial site is the place in between the atoms or which is available in your crystal lattice. So when you put constituent atoms in those sites, then it is called an interstitial defect. So now you are adding atoms. Adding atoms means the density will increase. So this is like common sense. Vacancy defect, density decreases. Interstitial defect, density increases. Then you have the most important that you generally discuss, Schottky defect. In Schottky defect, remember very easy, equal number of cations and anions are missing from the lattice site. In Schottky defect, equal number of cations and anions are missing from the crystal lattice. In this, generally the sizes of cations and anions are comparable. In this and because equal number of cations and anions are missing, so what happens to the density again? It decreases. Okay, stoichiometry is maintained. मतलब हर एक जैसे अगर NaCl में if you obtain, if you see the Schottky defect in NaCl, then for each of the Na जितने Cl होने चाहिए उतने ही रहते हैं. And for each of this, so that stoichiometry is defect. That's called stoichiometric defect. And in the stoichiometric, the last one is Frenkel defect. In Frenkel defect, what happens is one of the cations are smaller in size, anions are larger in size. So one of the cations leaves its lattice position और वो lattice position छोड़ के किसी interstitial position पे आ जाता है. In Frenkel defect, one of the cations leaves its normal lattice position and it comes at the interstitial site. So that is why in Frenkel the density remains same because nothing leaves and nothing gets added up. Okay, so Frenkel defect. Now in impurity defect कैसे होता है? Look up. जैसे you have a crystal of NaCl, ठीक है? Now I am going to replace this Na with some other similar sized atom like Sr, strontium. Strontium is of similar size, so I will have to add a compound strontium chloride to it. ठीक है? So what will happen? Na has a charge of +1, Sr has a charge of +2. So for 2 Na plus, अब मेरी दो लैटिस साइड्स ऑफ Na प्लस विल हैव टू गेट वैकेटेड फॉर 1 Sr2 प्लस. ठीक है, तो इम्प्योरिटी डिफेक्ट में क्या होता है? आई लुक फॉर अ सिमिलर साइज्ड एटम विच मे हैव द सेम और अ डिफरेंट चार्ज. अगर वो डिफरेंट चार्ज है तो दैट मेनी नंबर ऑफ कटाइंस विल हैव टू बी रिप्लेस्ड. So 2 Na plus will get replaced with 1 Sr2 plus. So 1 Sr2 plus will come here in the vacant site and 1 vacancy will be created. So remember, in this case the number of vacancies will be equal to the number of sites occupied by Sr2 plus. Clear? हमने 2 Na plus हटाए और एक Sr2 plus डाल दिया. So the vacancy is going to be equal to, the vacancy will be equal to the number of Sr2 plus, क्योंकि जितने Sr2 plus डालेंगे उतनी vacancies create होंगी. एक और example है इसका, you have AgCl and which is replaced with Cd2 plus. So how many Ags will be replaced with Cd2 plus? 2 Ag plus will be removed and 1 Cd2 plus will be added and 1 vacancy will be created. So the number of vacancies will be equal to the number of ions of higher charge depending upon, जैसे यहाँ पे plus is getting replaced with 2 plus, so the number of vacancies in this case will be equal to the number of sites which are getting replaced or the number of impurities. Here you have a question also in your book only. If you have 10 to the power minus 3% of SrCl2 present in NaCl, if you have this many percentage of SrCl2 present in NaCl, what is the amount of vacancy created? ठीक है? The answer is very simple. The amount of vacancy created will be equal to the number of Sr2 plus. What is that? 10 to the power minus 3 divided by 100, because it is 10 to the power minus 3%. So the answer is 10 to the power minus 5. So the number of vacancies which are created are 10 to the power minus 5. Alright. Per mole. Right? Nahin. Then the next one, non-stoichiometric defects. Please quickly pay attention to this as well. In non-stoichiometric defects, what you have is up on the board. In non-stoichiometric defects, you have one as the metal excess defect and the other which is known as the metal deficiency defect. Clear? Look up all of you all. So you have metal excess defect. In metal excess defect, there are two ways. See, I take a crystal, the best example is NaCl. I take up a crystal of NaCl. अब मैंने उसका क्रिस्टल लिया and I heat it in sodium vapors. I will heat it in sodium vapors, तो क्या होगा? क्रिस्टल के ऊपर सोडियम आके थोड़ा थोड़ा सेटल हो जाएगा. कुछ atoms of sodium will come on the top. So what will happen? I am taking an NaCl crystal. You have NaCl crystal lattice है, मैंने सिर्फ NaCl लिखा है. I am heating it in sodium vapors. So what will happen? Some Na will come and sit on top. So what will happen? Under I have Na plus and Cl minuses. One of the some Cl minus will get attracted to this Na which has come on the top. So what will they do? They will lose their normal position. अपनी Cl minus वाली seat से उठ के they will go to the surface to form NaCl with this. So if Cl minus will come here, this will become Na plus electron. I repeat, I have a crystal of sodium chloride. I am heating it in excess of sodium vapors. तो कुछ सोडियम आके सेटल होगा टॉप पे, सरफेस पे, और जो अंदर से हमारा जो Cl minus है, that will get attracted towards this topmost surface Na. Once this get attracted, then your Na will form NaCl with it by losing an electron, and this electron will occupy the anionic site. ठीक है, whenever an anionic site is occupied by an electron, you call it an F center or a Farbin center. It is an F center. Clear? अब इस केस में क्या होगा, फिर दूसरे Cl minus को लगेगा, I should also do the same, right? Or what will it do? It will shift to this Cl minus and electron will come here. तो Cl minus इधर आएगा, electron इधर आ जाएगा. Then slowly steadily with another neighbor, it will ask to exchange its position. तो इससे क्या होगा, that electron will start conducting. तो properties enhance हो गई, क्योंकि electron move करेगा तो current generate होता है, पता है ना? So conducting properties increase हो गई. Then your electron also, because of this movement, it imparts color to the crystal, and the color that is imparted in case of NaCl is yellow, in case of LiCl is pink, and in case of KCl it's violet or lilac. ठीक है, इन सब में याद रखना the metal excess defect is because we are heating the crystal in the excess of cationic vapors. तभी cation आ रहा है, it's getting settled on the top, anion is leaving its position. अब anion ने छोड़ा तो metal excess में हो गया, anion goes to the top और anion की जगह पे क्या आ गया, electron, that F center. So if you get a question like the color in NaCl is yellow due to F centers, clear answer F center. एक और तरीका है metal excess, this is due to anionic vacancy. ये वाला जो first type discuss किया, that is due to anionic vacancy. The second thing that I am going to tell you is due to say excess of cations. And how do you get excess of cations? The example, the general example that very general that you take is that of zinc oxide. What you do is when you heat it a little bit, the zinc oxide crystal को ही जब heat करते हैं, so on a little bit of heating, it generates Zn2 plus half oxygen, that means oxygen gas is formed, plus 2 electrons. क्या होता है, oxygen gas है तो it escapes. So what will you have left over in your crystal? Zn2 plus. जितना Zn2 plus convert हो गया उतना oxygen उड़ गया. So this is again metal excess, and zinc oxide normal is white and after heating is yellow. That is because of metal excess defect due to presence of extra cations, due to the excess of cations. That is why metal excess. इधर metal excess क्यों था, क्योंकि anions ने अपनी जगह छोड़ी, इधर cations extra present हो गए because the anion left. Okay, and that position will again be occupied by the electron. So basically here generally depends upon how the gas is getting vaporized to the atmosphere. Now for the metal one is metal excess and the other is metal deficiency. So when you talk about the metal excess and non-stoichiometry, one thing that we've talked about here, and the other non-stoichiometric is like metal deficiency. Consider the example of FeO. Iron oxide में what happens is this is -2 and Fe is in the +2 form. होता क्या है, कुछ +2 जो है Fe2 plus they get lost or they get moved out of the crystal lattice. Now in order to compensate for that loss, some of the Fe2 plus get converted to Fe3 plus. Fe2 plus can easily get converted to Fe3 plus an electron. So जब ये shuffling हो रही होती है, the balance of the charges, because of this balance of the charges you have some of the Fe2 plus and some of the Fe3 plus, which spoils the stoichiometry. Stoichiometry खराब हो जाती है. If you have FeO, this is 1:1. Here when this has a mixture of Fe2 plus and Fe3 plus, you get compound of the type Fe 0.93, 0.96 and so on in comparison to O. So the formula becomes Fe 0.93 or it can be Fe 0.96 O. Nickel oxide में भी यही case है. So there you can have Ni 0.98 O and so on. These are your non-stoichiometric compounds. Now here you get a question. What is the question that you get here? You have a formula of Ni 0.98 O. ठीक है, अब इसमें straight away पूछते हैं, you tell the number of Ni2 plus and Ni3 plus. Straight away the question is put as this. So how do you take care of that? देखो जितना charge, this is a crystal which is stable. Understand this? Here the charge on the oxygen atom will be equal to the total charge of the cations. ठीक है? So let oxygen is 100% and nickel is 98%. ठीक है? तो अगर ऑक्सीजन के एटम्स 100 मान लोगे तो टोटल ऑक्सीजन पे चार्ज कितना होगा -200. तो टोटल निकल पे चार्ज कितना होना चाहिए +200. ठीक है? अब मान लो कि Ni3+ के x एटम्स है तो Ni2+ के कितने एटम्स होंगे 98 because this was 98 and your oxygen was 100. We considered for every 100 atoms of oxygen we had 98 atoms of nickel. So this becomes x and this becomes your 98 minus x. So this can be easily solved as you can have the total charge to be equal to 200 क्योंकि ऑक्सीजन का -200 है तो टोटल निकल का कितना होना चाहिए +200. So here you have 3+ atoms be x. So the charge is +3x plus 2 into 98 minus x is equal to 200. Got it? So you can easily find out. So what you have is 3x plus 2 into 98 is 196 minus 2x is equal to 200. So x is equal to 4. So similarly you can find it out for Fe or Ni or any other atom. Remember यहाँ पे सिर्फ charge balance करना है. Charge balance करके form the equation and then do it. Alright? Then we are just left with the magnetic properties and types of semiconductors. Types of semiconductors, you have extrinsic, intrinsic and the various types that we will cover up in the next class then. Thank you.